5.5, derivative and integrals of base A. But before we learn anything new, we need to remember the old, which we did a good job yesterday of, well, not yesterday, but the last time we met of running through this. What is the derivative of u to the n? N times, wow, you sound like a broken record. What? Only like really broken, not working. What is it? N times u times u to the n minus 1, and then u prime. What's the derivative of natural log of u? U prime over u. The derivative of e to the u? E to the u, u prime. Derivative of sine of u? Cosine of u, u prime. Derivative of cosine? Negative sine of u, u prime. We'll have to start writing small here in a minute. Derivative of tangent? Secant squared u, u prime. Derivative of secant? Secant of u, tangent of u, u prime. Cosecant? Negative cosecant of u, cotangent of u, u prime. And the integral, the derivative of cotangent? Negative cosecant squared u, u prime. All right, well, if we know the derivative rules, what do we know? The integration rules. And there's a few that are a little different, but like we have the integral of secant and cosecant down here. What is the integral of u to the n? And u to the n plus 1 over n plus 1, and then plus c. The integral of u prime over u, or the integral of 1 over u du. Natural log of the absolute value of u plus c. Integral of e to the u, love that one. E to the u plus c. Integral of cosine. Sine of u plus c. Integral of sine. Negative cosine of u plus c. Integral of secant squared of u du. Tangent of u plus c. Integral of secant tangent. Secant of u plus c. Integral of secant cotangent. Negative cosecant of u plus c. Getting lazy about saying the angles here. Integral of cosecant of u squared. Negative cotangent of u plus c. If you leave the plus c's out on your memorization quiz, which I'm sure everyone's going to get a perfect score with at least what I'm hearing. Now, the integral of secant of u du. It's a natural log of the secant of u plus tangent of u plus c. There's a couple rules up here. I realized I didn't get up the integral of tangents and the integral of cotangent, which will obviously fill that in. But the derivative of secant of u is secant, positive secant tangent. It's not an inverse relationship, but the integral of the secant of u du does have the same two trig functions of secant and tangent. They're added inside a natural log function, and there is no sign change for the integral of secant, just like there is no sign change for the derivative of secant, which makes the integral of secant of u du negative natural log of cosecant of u plus cotangent of u plus c, and the integral of the tangent of u du, which if you forget, you're integrating sine over cosine, which is a, you can easily manipulate into the form of u prime over u. So what is the integral of tangent of u du? Negative natural log of the absolute value of sine of u plus c. That's cosine. And the integral of cotangent of u du, which is the integral of cosine over sine, is going to be the natural log of the absolute value of sine of u plus c. Perfect. Okay, so to this list, we are going to add a few more. Whoop, whoop. So derivative and integrals of base A. So let's say we've got y is equal to a to the x, and we want to find out what y prime is. Now I'm writing this as an equation because this is what we're learning. We're about to create a rule that is the derivative with respect to x of a to the u power. It is just a rule, and if you have it memorized, then great. But, you know, that's a lot of rules over there. Some of these are easily derived, like we derived the integration rule for tangent and cotangent the other time we met, and so on and so on. You can derive other ones as well, but it's beyond the scope of today. So let's say you're taking the test and you forget the derivative of a to the u. You can set it equal to an equation, and this is a constant base of some unknown constant base of a to a variable exponent. And today, as we do our examples, you're finally going to realize why I keep emphasizing with these derivative rules. I say over and over again, I've been saying that we're taking a derivative of a variable base fixed power, and there's a that's power rule, right? And we have a derivative of a fixed base variable power. This will be another fixed base, but not e. The technique I'm going to use right now to derive this derivative formula for a to the x is the same technique that you're going to have to use when you have a, say, variable base and a variable exponent. There's no rule for this. Okay? The only way that you can do a derivative for a function where the base is a function and the exponent is a function is through something called implicit differentiation. But we'll hit that in a minute. Do we know how to take a derivative of a fixed base other than e to some function? Of course, the answer is no. So we need to write this in a format that is not a fixed base other than e to a variable function, and we're going to do that by applying a natural log to both sides. And why natural log? Because we have a derivative rule, a derivative rule and an integration rule involving natural log. We don't have a derivative and integration rule involving log base a. It's log base e. So we're going to take the natural log of both sides and get the natural log of y is equal to the natural log of a to the x. Why is this desirable? Because the natural log of a to the x, we can use the power rule of, or property, if you will, of natural logs and move this variable base out of the location of the exponent. And we're going to have the natural log of y is equal to x times the natural log of a, and we're going to take a derivative implicitly of both sides of this equation. We're going to apply a natural log and opens the door to implicit differentiation, which is going to make this derivation possible and not that, really honestly, not that complicated. We're going to take the derivative of both sides with respect to x. Now, before I write the right-hand side, let me emphasize here, this variable of a is an unknown constant. And when you take the natural log of a constant, you get another constant. So this is I'm only writing this for notes. I really like the x times natural log of a orientation better, but it's the natural log of a. It's just the a that's inside the natural log, and it's times x. So we're taking on the right-hand side the derivative with respect to x of a constant times x. So what's the answer to the right-hand side? Just the natural log of a. It's like the derivative with respect to x of 2x is just going to be 2, right? Because the 2 is a constant. Well, the natural log of a is a constant. We just don't know what that constant is because we're writing a formula that will work for any constant base of a. But it is just a number. So the derivative of natural log of a of x is just the natural log of a. Of course, on the left-hand side, we have the derivative with respect to x, and the independent variable of natural log right now is y. So what's the derivative with respect to x of natural log of y? 1 over y. And if you finish the chain rule, come on, this is not new. dy over dx, which I wouldn't even be writing, but no one's giving me like a choral answer. Just a few of you are whispering for some reason. The derivative with respect to x of natural log of y is y prime over y, and that's equal to the natural log of a. Well, this journey started with me saying y is equal to a to the x, and the intention of this little derivation is to find y prime. So I need to solve this, and as I told you last semester, when you do implicit differentiation, which is what we're doing here starting with line number 4, your implicit differentiation is not done until you've solved for y prime. So we're going to multiply both sides by y prime and get y prime is equal to y times the natural log of a. And if we remember what y was in the first place, y was a to the x. So we have y prime is equal to a to the x times the natural log of a. Or in other words, the derivative of a to the u is the natural log of a times a to the u prime. I'm adding in an extra u prime because I'm setting this rule up involving chain rule, as opposed to over here, the independent variable was x. But it is the same thing. So now you have a new derivative rule. And by the way, I hope you realize that, of course, there is a similarity between the derivative of a to the u and the derivative of e to the u, because it's still a constant base variable exponent. It's still a constant base variable exponent. What's the derivative of e to the u? E to the u prime. Part of the derivative rule of a to the u is a to the u prime, just like it was e to the u prime. We just have an extra little factor of natural log of a that showed up through the derivation process. Okay. We're not really, we kind of technically didn't take a derivative of a to the u. We really took the derivative of a constant times x and the natural log of y to get to this final answer. So that's a new derivative rule you have to memorize. If you memorize it, it's just that. If you don't, take the natural log of y of both sides, implicitly differentiate, and you're done when you've resolved for y prime. Y is equal to log base a of x. Calculus derivations at 7:45 in the morning. It's fantastic. Do we have a rule for taking the derivative of log base a of x? We don't. We're going to create one, but for right now we have a derivative for log base e, not log base a. Raise your hand if you remember the change of base formula. Yeah, like two of you are, not even one of the two hands going up, I'm not even sure if you're positive of your answer. So if you have a log and a base that you don't want to work with, there is a change of base formula, but I don't teach by memorization, which makes sense why almost nobody remembered what that formula was. So how about we write this logarithm as an exponent? What do you get from a logarithm? An exponent. And the base of the logarithm is the same as the base of an exponential function for these inverse math operations. So y is equal to log base a of x. The base of a logarithm is the base of its inverse math operation, that exponential function. You get exponents from logarithms, so we have a to the y is equal to x. And now let's solve this equation for y. You know, we learned logarithms in Algebra 2 and pre-calc to be able to solve equations, most of them financial, for us anyway. In biology, it might be growth of bacteria or decay of carbon-14 or something. But we want to solve this equation where the variable is in the exponent. That's one of the main purposes of learning logarithms in Algebra 2 and pre-calc. So let's take a logarithm, apply a logarithmic function to both sides in a base that's friendly to calculus, which is natural log. So you take the natural log of both sides. That allows you to, once again, power. We get not derivative or integrals using power rule, but the power rule for or property of logarithms, or whatever you want to call it. We have y times natural log of a is equal to the natural log of x. And now we have y is equal to 1 over the natural log of a times the natural log of x, which means that y prime is 1 over the natural log of a. Remember, a is an unknown constant, not a function. And we can let that constant coefficient applied to our natural log function stay in front of the derivative operation. And all of a sudden, we had a log base a base that we couldn't work with, turn into just a natural log. So what's a derivative of natural log of x? 1 over x. So we have y prime is equal to 1 over the natural log of a times 1 over x. So we have a new derivative rule. I'll write it as a chain rule, but the derivative with respect to x of log base a of u is 1 over the natural log of a times u prime over u. So you can quickly derive these two rules, derivative rules, if need be on a standardized test. You know, if you forget where the natural log of a is, sometimes it's a multiple, sometimes it's a division. You can derive it, doesn't take that long. You just have to know how to do implicit differentiation. The next rule is a little bit harder to derive. And you know, and for some of us, this will be the last math class. We're just trying to get this AP credit, this college credit, wherever you're learning this. And it might be your last math credit period if you're doing like a liberal arts degree. And some of us need to move a lot farther through mathematics. The farther you go, the more you're going to need to understand how this stuff all intertwines, you know, and actually understand this material as opposed to just doing memorization. So how do we integrate a fixed base of a to the x? Well, there's no rule for that. So we need to get this into a base e, not base a. So we kind of need to go off to the side and say y is equal to a to the x, and once again do some math to get this to be a base from a base a to a base e, which is going to involve, like our first derivation, natural log. So we have the natural log of y is equal to the natural log of a to the x. Now ultimately I need an integrand. You know, I need to solve for y so I have an integrand that is in a base that I can work with. Okay, so I'm not going to like take a derivative right now because I'm not trying to derive a derivative formula. I'm trying to derive a formula for integrating a to the x dx or a to the u du. So how do I get rid of this natural log that I just applied? Which seems like it wouldn't be what I want to do, but I want to solve this for y. So how do I get it out of the natural log function? Apply a base of e to both sides. Now, don't cancel the logarithm. I probably misspelled that, I'm sorry. Don't cancel the natural log on both sides. You're trying to get an expression that is set equal to y. So we have y is equal to e to the natural log of a to the x. A to the x was originally equal to y, and now we have e to the natural log of a to the x is equal to y. So I've written this exponential function base a now as an exponential function base e. If you're not totally understanding this, just pay attention and take the notes and let it sink in later. You don't have to do this derivation on any problem. but I'm trying to give you some tools to recreate these formulas if you forget them. Some of you I know are just going to memorize this, and some of us are going to actually have to understand this for later, more advanced mathematics following this course. What is the integral of e to the u? Du. It's e to the u. The integral of e to the u du is e to the u plus c. So if we have a u, we need a u prime or a du. And right now, we just created an exponent of e. We just created a u that is the natural log of a to the x, and we need, if possible, to create a du. I'm going to complete the chain rule for this integral. I'm not going to do a full-blown u substitution. I'm going to this time show you how to complete the chain rule if it's possible. What should you do? I wrote du here, but we need to do some work. Our intention is to find du, but what should you always do before taking a derivative of a logarithm? Expand or separate. So we're going to use, again, power and expand this logarithm, and we have u is equal to x times the natural log of a. So if u is x times the natural log of a constant times x is u, what's du? Just the natural log of a. You know, dx, if you will. So this integral, this is the integral of u. And if this is a u, we need to introduce a u prime. I want to create, and this will be the first time I've done this in class, so it is going to be different and maybe confusing to some of you, but I'm trying to set up the integral of e to the u prime. Du is another notation for u prime. It basically means the same thing, only this is kind of more appropriate for integrals, integral notation. So we have an e to the u. Outside e to the u, we need another factor of u prime. Well, u prime is the natural log of a. And if you want to have the dx there for full-blown u sub, you know, whatever. But natural log of a is u prime. So to this integrand, so if we have an integral of e to the u, our u prime is the natural log of a. So we're going to have to introduce a factor of u prime to this integrand. So we're going to have to multiply this integrand by the natural log of a. So now we have the integral of u prime. But I just can't change the value of my integrand. I can make it look different, but I can't change its value. So if I'm going to multiply by the natural log of a, which is a number, we need to divide by the natural log of a, which is a number. Just like you did, or you do when you're adding fractions, right? You take some fractions and multiply them by maybe 2 over 2 or something like that to make them look different, but not be a different value. So we have 1 over the natural log of a times, what is the integral of e to the u prime? Remember that u prime shows up through the chain rule process, so it'll just disappear through the integration process. What's the integral of e to the u prime? E to the u. So we have 1 over natural log of a, e to the u, which is natural log of a to the x plus c. But now let's clean things up a little bit. We created the base of e to allow this integration to happen. But now that the integration is done, exponential function base e and log base e are inverse math operations. Let's let those inverse math operations cancel out. And we have 1 over the natural log of a times a to the x plus c. Or in other words, the integral of a to the u du is what? 1 over natural log of a times a to the u plus c. Bam! I love these derivations. I did when I was a kid. I'd be like, oh, just give me the formula. Put my head down, go to sleep, like some of, well, actually, this class is really actually quite good. I can't harp on anybody in here. What? Oh, you do go to sleep while I'm teaching? Oh, hey. So now we're just going to start running through a whole bunch of examples. I mean, in the end, once you have these these two new derivative rules and integration rule, if you know them and if you are good with all your other derivative and integrals, the homework's going to go quite quickly. But through this derivation process, we get to refresh our implicit differentiation and just hopefully get a deeper understanding of what is going on. So for our first example, these are going to be in groups. We have example number 1. We're going to be taking a number of derivatives of a to the u. So we have, for our first example, y is equal to f of x. Let's say y. Y is equal to 2 times negative 5 to the x. And we want to find y prime. Well, what's u in this problem? Negative 5x. Then what's u prime or du? Du and u prime mean the same thing. Just negative 5. So if y is 2 to the negative 5x, if we just straight up immediately realize that this is a constant base of a, and I don't know, if you want to write that for notes, your a is 2. What's y prime? It's natural log of 2 times 2 to the negative 5x power times, but I didn't give myself very much room, times negative 5. So your final answer is y prime is negative 5 natural log of 2 times 2 to the negative 5x power. And once again, though, if you did forget this, if you forgot that rule, you can take the natural log of both sides, bring down the exponent. So you can bring the power down and have negative 5x times the natural log of 2. Take the derivative of both sides with respect to x, and you have y prime over y is equal to, of course, we have a y prime over y because we're taking a derivative with respect to x, not with respect to y. If it was to y, it'd be 1 over y. Negative 5 and natural log of 2 is a constant times x. So the derivative of negative 5 natural log of 2 times x with respect to x is just negative 5 natural log of 2. Swing the y back over and solve for y prime, and you have negative 5 times the natural log of 2 times what y is equal to, which was 2 to the negative 5x power. Really not, it's really honestly about the same amount of writing. Now, if you get really good at this practice and you get really good at the use of the derivative formula, you're not going to need to write your u prime, and a. But you have 3 lines of black work that you're writing, or 2 lines maybe, when you have the rule, and you got 1, 2, 3, 4, 5 lines of work if you do implicit differentiation. So a little bit more work that way, but you're not memorizing a new formula. Let's take a look at another example. And maybe I'll give you a few minutes to work on this yourself. We'll take a look at y is equal to, for our second example, y is equal to x times 3 to the 2x power. Let's try and figure out what y prime is equal to. Who wants to help me out? Woo! Y prime.
So start by knowing that you're going to have to use the product rule.
Product rule. All right, Mr. Specific. Very good. Product rule.
So derivative of x is 1, so that first thing is going to plus x times the derivative of 3 to 2x. So that's going to be the natural log of 3 times 3 to 2x times the derivative of that 2x.
Cool. So we have the derivative of the first factor times 3 to the 2x, leave that second factor alone for the first term, plus x times our base is 3, or a is 3, so natural log of a and natural log of 3. And then kind of go back to that derivative of e to the u. The derivative of e to the u is e to the u prime, but of course it's not e, it's 3 to the 2x, but it's the same thing. We've already taken care of that base of, that base is not equal to e here with the natural log of 3, so 3 to the 2x times 2. Perfect. And there's no need to clean that up unless you're, I don't know, I'm just going to do it for notes, but we have 3 to the 2x. Let's see here, we've got 2, so plus 2x times the natural log of 3 times, and maybe even wrap that 3. I really always try and emphasize with parentheses what is actually in the natural log function. We don't want to think that this other base of 3 is also in the logarithm. 3 to the 2x. Excellent. Let's take a look at another example. We'll throw a little trig in here. Let's take a look at evil, fun.
I like trig, I'm sorry.
Trig is like so amazing. It's only the study of two things, angle in, reference triangle out, parts of a triangle out. We have y is equal to 5 times negative 2x times the sine of pi x. Give that a shot. Who's up?
Okay, well, you're going to have to use product rule on this one.
Yeah, you are. Woo!
Okay, so for the first term, you're going to want to take through 5 to the negative 2x, which is going to be the natural log of 5 times 5 to the negative 2x times negative 2.
Beautiful. So natural log of 5 times 5 to the negative 2x times 2.
And all of that times sine of pi x.
And then plus.
Plus, then pi cosine pi x.
Okay, so you're taking here we're taking the derivative first. Okay, so the derivative of sine is cosine. So we have the derivative of sine is cosine of pi x.
And you want to do the chain rule on that to bring the pi out.
Beautiful.
And then all of that is just times 5 negative 2x.
Beautiful. And there is not any points awarded for simplification on a free response question. And other than factoring out 5 to the negative 2x out of our two terms, there isn't much that will simplify. So I'm going to leave this like this. Maybe in multiple choice, this common factor might be something where they factored it out, maybe even put it in the denominator, but our derivative is done. So let's go. All right, so here we go. Enough. All right. All right. So for our next example of the many that we're going to do today, we've got y is equal to, so we have y is equal to 2x raised to the power of sine of x, and we need to take the derivative. So this will be the first time this year that you have seen a variable base, variable exponent. Now we don't have, any base of a's in here, so we're good to go, but we do not have a fixed base variable exponent, and we do not have a variable base fixed, did I say that wrong? We do not have a variable base fixed exponent or a fixed base and variable exponent. It is both the base and the exponent, which are functions. So there is not a rule to take this derivative. The only way you can take this derivative is through logarithmic differentiation, which I mentioned as a footnote earlier this year, and I said logarithmic differentiation was good for when you have a function with a lot of powers and multiplications and divisions, and you can use logarithms to expand all of that. Well, it's the same thing here. We're going to expand this exponent to an exponent with logarithms and get the natural log of y is equal to the natural log of 2x raised to the sine of x. That natural log applied to the base of 2x sine of x is going to allow us to use the power property to bring that power of sine out front, because again, what do you get from a logarithm? An exponent. So this is an exponent coming from natural log of 2x raised to another exponent. And when you have those stacked exponents, you can multiply them. So we have natural log of y is equal to the sine of x times the natural log of 2x. And now we're taking that implicit differentiation process to both sides of this equation, which is now not just solved for y. We're not doing explicit differentiation. So the derivative of natural log of y with respect to x is what? Y, you all should be saying this together, y prime over y. I know you know the answer to that. And on the right-hand side, you're taking a derivative of a product of two functions. And for this example, even though I just did a lot of it, we just discussed the derivations of a lot of derivatives and integrals involving base a, these really are just old familiar rules that we already know. What's the derivative? We have y prime over y. What's the derivative of sine? Cosine. So cosine of x times the natural log of 2x plus, now leave your first factor alone, sine of x. What is the derivative of 2x with respect to x? 2 over 2x, which of course those 2's are going to cancel, giving us 1 over x. And are we done with this problem? No. What's the last step? You have to solve for y prime or move the y over to the right-hand side. So we have y prime is equal to y, which was originally 2x raised to the sine of x power, and then times, well, what we got is an answer. Cosine of x times the natural log of 2x plus sine of x times 1 over x. And that's the end of that example. So that's the end of the rules, the examples involving the derivative of a to the u. So we have y is equal to log base 5 of 4x squared plus x. Try and work that out. We have already derived this, but if you want that change of base formula, log base, what is this formula? I don't even know what it is. Log base a of x is
1 over the natural log of a.
No. The change of base formula.
Oh, isn't it? It's a base.
Log base a of b is.
Oh, log base b over log, or log.
Hey, good morning.
Over log a.
Log
Isn't
base,
it b over
whatever base you want to use,
Oh, yes.
of b over log base, whatever base you want to use of a. Good morning. Hey, good morning. So if you if you have y is equal to log base 5 of 4x squared plus x, we need to either use the change of base formula to put it into a base that we want to work with, which is natural log of log base c or natural log, or just use our derivative rule where the derivative of with respect to x of log base a of u is 1 over natural log of a times u prime over u. So give that a shot. We can, if you so desire, you can change this base of 5 into any base you desire, such as natural log. So you can change this base of 5 to be y is the natural log of 4x squared plus x over the natural log of 5. And then y prime is going to be 1 over the natural log of 5. And then because you have a natural log function in here, you can do that u prime over u formula that we've been practicing a lot recently, which is going to be 8x plus 1 over 4x squared plus x. Or, I mean, changing the base of logarithms, okay, granted, I didn't teach the formula in pre-calc. We wrote these logarithms as an equation like you saw me before. Most of you left for the pictures. We went from logarithmic form to exponential form and solved that equation. But it is just log of whatever base you want to work with. The b seems to be over the a, and voila, natural log of b over natural log of a is your conversion. Or your a is equal to, your a is equal to 5, and your u is 4x squared plus x. You know, I'm still doing exactly what I always do, but for some reason, you know, they all walk in, you're like, oh shit, am I going to say something wrong? You know, it's just the school superintendent, whoever that lady was. I said a bad word. So you have 1 over natural log of a times u prime over u. So whatever you want to do, a direct application of the rule or convert into natural log. Honestly, because I teach math and I do a lot of derivations, I prefer the going into natural log with change of base formula, but it is the same thing. And I'll give you one more example to try on your own, just because that was a little bit of hesitation plus the interruption.
That one was too easy. Can we get a harder one?
But I hope you feel like these are all easy, because we're just cycling through the same process over and over again of that derivative integration process with different types of formulas. We have, as another example, y is equal to log base 3 of the square root of 3x squared plus 1, which may look more complicated, but as I said, what's the first step of taking all derivatives? Expand. So if you expand this correctly, it should really not be any more complicated than this first example. You just have to deal with that square root function, that radical notation. So we have y is equal to log base 3 of 3x squared plus 1. You said you expanded, but hopefully you wrote the radical first as a power of 1/2. Now you're going to do that expansion, which is, what do you do with that 1/2? Bring it out as a multiplication, a power. Bring that power down as a multiplication. We have y is equal to 1/2 log base 3 of 3x squared plus 1. And we have y prime is equal to, so 1 over 2.
1 over 2, and then parentheses.
Okay.
Okay. 1 over
You got this.
the natural log
Of?
3.
Good. You're doing great. Keep going. So your u is 3x squared, and you're correct that u prime is going to be 6x. Nice job. Over?
Over 3x squared plus 1.
Beautiful. Yes, that deserves. So our final answer is 1 over 2 natural log of 3, excellent job, times 6x over 3x squared plus 1. Very, very nice job. One more problem involving these derivatives. So we still have about 25 minutes left, and I like to build up the problems to be quite difficult. So we've got y is equal to log base 3 of x squared times the square root of 3x plus 1 over 5. So we have obviously a lot going inside of our logarithm. You know, this looks very complex. This looks very difficult. These type of problems, if you just had y is equal to the square root of y is equal to x squared times the square root of 3x plus 1 over 5. And especially if this 5 were like a 5 sine or a 5x, well, it wouldn't be an x you could cancel, but this would be a perfect candidate for logarithmic differentiation even if there wasn't a log in it. Because the logarithm, once you apply it to both sides, would allow you to do what? With all of this multiplication, the division, and the radical, you need to do a lot of expansion. So in its current state, this problem is quite difficult. There are three, even though I made them all the same color, there are three functions you should be thinking about expanding with, and basically making this not one large logarithmic function, but three small, simple logarithmic functions. So expand this out before you do anything, and you got three little simple problems. All right, give it a shot. Who's going to help me? I think her hand was actually because she was talking with her hand, but help me out. What'd you do first? Expand it. Blow it up. Y is equal to what?
Log base 3 times and then x squared.
Mm-hmm.
And then plus.
You're going to expand this multiplication. We have a multiplication with a like base, so we're going to add those exponents. So plus.
Log base, wait, 1/2 log base 3.
Oh, I'm going to go ahead and do it in two steps. That's correct, but log base 3 of 3x plus 1 to the 1/2 power.
And then minus log base 3 of 5.
And then log base 3 minus log base 3 of 5. Then we're going to bring both, maybe you don't, I mean, you might say you don't need to or you didn't, but I'm going to bring both of these powers down and write basically what you just said. We have y is equal to, not basically it is, 2 log base 3 of x plus, there's the 1/2 you mentioned a second ago, 1/2 times log base 3 of 3x plus 1 minus log base 3 of 5. And what did you do for your next line of work? Did you just write the answer, or?
I just like wrote everything 1 over ln of 3 and plus.
Like you went in and just wrote the derivative out. Okay, so I feel like maybe tomorrow or the next, no, I don't see tomorrow, but the next time we come together, I might be doing some of these and just write them as natural logs and change the base as opposed to applying that rule, even though we have it, and say y prime.
It would be
2.
1 over 2 ln 3. Wait, 2 times 1 over ln 3. Then I did times 2x over x squared.
Oh, I did the expansion. So I'm going to have, with this expansion, we'll have 1 over x. Okay, so you had the same thing, just a slight variation.
And then I did plus 1/2, 1 over ln 3. And then times 3 over 3x plus 1.
So we had the 1/2 coming down. We have a base of 3, so 1 over the natural log of that a, that base, 1 over natural log of 3. And then with our u being 3x plus 1, we have a u prime, 3 over 3x plus 1. And then that's a constant. The log base 3 of 5 is a constant, and the derivative of a constant is equal to 0. And that is your final answer. I mean, we do have a common factor of 1 over natural log of 3. There's a number of ways we could simplify this, but the only reason, again, I keep saying this over and over again, but the only reason to go past this is to match a multiple choice answer. And if I had a lot more time and not many examples, I might do that, but this is good. Nice job. Another example. We've got the integral. So now we're moving into our integration rule. We have the integral of 7 to the negative x dx. Do we have a composition of functions? What integration rule? So we have the integral of 7 raised to the negative x power dx. What integration rule does this look closest to? We've got a lot of integration rules over here, but integral of a fixed-based variable exponent. So for this problem, what is going to be our u? Negative x. what's our du going to be? Negative 1 dx. So let's just go ahead and complete, like, this is ultimately, I hope you find to be a very easy integral. And we're in the middle of chapter 5 now. As you continue to come into class, I'm going to do more and more completion of the chain rule. But I don't think I want to do that quite yet for this one. We have negative du is equal to dx. So doing a full-blown u sub, we've got the indefinite integral. The dx is going to come out and be replaced with negative du, and we have 7 to the u power. So what is the integral of a to the u du? 1 over natural log of a times a to the u plus c. So we have a negative. We have negative what? Negative 1 over natural log of a, so negative 1 over natural log of a is our base, so natural log of 7 times 7 to the u plus c, or our final answer will be negative 7 to the negative x, because that's what we set to be our u, over the natural log of 7 plus c. Let's take a look at an integration problem that's just a tiny bit more sophisticated. Here we have, for our next example, we have the integral of x times 3 to the negative x squared dx. Give that a shot. All right, so for this one, we're going to complete the chain rule as opposed to doing a full-blown u substitution, okay? So if we were to do a u substitution, well, first of all, we need to look at this integral and say, what does it look closest to? We do have a multiplication of two functions, but that hopefully has been created with the chain rule process in the derivation process, and we have a base, a fixed base, and a variable exponent. And so obviously no trig, it's not a fixed base of e, there is no division, so it probably will not be integration involving a natural log, and the base is not a function, the base is a constant. So really, if we cannot make this rule now, this new rule work, we might have something that we cannot integrate. So it looks like we're using this rule. So if we're going to be able to apply this rule, the integral of a to the u du, what is u going to be? It needs to be that exponent. It needs to be nice. We need to let u equal negative x squared, so then du is going to be negative 2x dx. Well, that's exciting because, you know, once we determine what u is, which is always where's u going to be? Inside a composition. And here we have this function inside of an exponential function in that exponent. Outside that composition, we need to find this function. And we do have a linear function. To complete the chain rule, to complete a, we have a u in the exponent. Let's create a u prime outside of the exponent. We need an additional factor of negative 2. So I'm going to leave a little space, and we have the indefinite integral of x times 3 to the negative x squared dx. Our u is that exponent that's on the base of 3. We're going to create a u prime outside of the exponent. We need a negative 2 to go along with the x. I'm going to multiply by negative 2. But if I multiply a numerator by negative 2, even though it doesn't look like this is a fraction, if I multiply the numerator by negative 2, we have to multiply the denominator by negative 2, or divide by negative 2. And that is a multiple of 1. Multiplying by 1 makes things possibly look different, but not change their value. What is the integral of a to the u prime. du is u prime, means the same thing. The integral of a to the u prime, the integral of a to the u prime is, let's not forget the negative 1/2 that's already out there, is what? 1 over natural log of 3 times, you need to keep going, times 3 to the negative x squared plus c. Bam! It's the last example. The definite integral from 0 to pi over 2 times the 5, the definite integral of, from 0 to pi over 2 of 5 raised to the sine of x times 2 cosine of x dx. What? We have a multiplication in our integrand, and there is, at least for our class, we've not learned integration by parts, so there is no product rule for integration, except there is something called product integration by parts. So our only multiplication of two functions that we can deal with has to be a creation of u prime through the chain rule process. So we need a u and we need a u prime outside that composition to have that chain rule pattern, to have the possibility of a u sub working. What does this look like? Is it going to be just an integral of cosine? Is sine? Or, wait a minute, what do we have in this other factor? A constant base of 5. And we have an integration rule for when we have a constant base to a variable exponent. And we have that constant base of 5 to a variable exponent of the sine of x. So what is going to be our u? Probably going to be sine of x. And what is then going to be our du? What's the derivative of sine of x? Cosine of x dx. At least, you can include the dx if you're going to do a full-blown u sub with that integration notation. Well, what do we have outside of our composition? If this is our u, what do we already have outside the composition? We have a almost u prime. We have a cosine of x outside the composition. So we're looking really, really good. But this is cosine of x dx, and we have a 2 cosine of x dx. Well, this 2 is not going inside of a trig function. It's not inside of an exponent. It's just a... So what can you do with constant coefficients? Move it out in front of the integral notation, or derivative notation, or limit notation. So if I just move the 2 out in front of our definite integral, we have 2 times the definite integral from 0 to pi over 2 of 5 raised to the sine of x power times the cosine of x dx. This is already in the format of a to the u prime. There's really no reason to go through the full-blown u substitution process. This is already the integral of a to the u prime. And remember, the u prime shows up through the derivative rule involving chain rule. Thus, when we integrate, the u prime is just going to disappear. So the integral of a to the u prime, the integral of a to the u prime is, help me out, come on. So we have 2 times 1 over the natural log of 5 times 5 to the power of sine of x with an upper limit of pi over 2 and a lower limit of 0. Plug in the upper and lower limit. And also, I'm going to go ahead and this 1 over natural log of 5 is a constant coefficient. I don't really want to deal with it through the whole rest of the problem. like repetitively through the arithmetic. So I'm going to bring that constant coefficient out with the 2. And we have 2 over the natural log of 5 times 5 raised to the sine of pi over 2 minus 5 raised to the sine of 0. Don't be too quick to assume that when you plug in 0, your answer is going to be 0. We have 2 over the natural log of 5 times, what's the sine of pi over 2? 1. So what's 5 raised to the first power? 5. Minus, what's sine of 0? 0. But it's 5 to the 0 power. Anything to the 0 power is 1. So we have 4 times 2 is 8 over the natural log of 5, which is a really surprisingly simple looking question for such a complex looking definite integral. And that is the end of our many, many examples. Bam! Go do your homework.
All right, cut the cameras.
What's that? Cut the camera. Yeah.